Hello, everyone. I'll just start out by saying that I have never, ever done anything even resembling something like this before. So I'm quite nervous, but I'm also very excited that all of you are here today, because at Far North, we are super hyped about dots, and obviously, we are not alone. Welcome to this talk, Creating a Third-Person Zombie Horde Shooter Using Dots. My name is Simon, and I am the game director at Far North Entertainment, which is a small game development studio from Gothenburg in Sweden. For the past year, we have been developing a post-apocalyptic, cyberpunk-themed zombie survival game, which is not just about the scarce survival, but also about facing off against hordes of thousands and thousands of enemies. And in order to realize this vision, we had to use dots in our game. We have two goals with this presentation. The first one is that someone who might never have even used dots before will have a good general understanding for dots and the general concepts and why it is so powerful. The second goal is to show you all a concrete example of how we took dots and implemented it in our project. The presentation is divided into 3 parts. The first part, I will show you some gameplay footage so you get a better context for what we are doing. Then we will go into the more technical part, where I will first talk a little about the problems that we faced and how then we solved those problems using dots. And then I will just wrap up the talk in a quick conclusion section. So, Project FNZ, because we don't have a name for the game yet. Let's take a quick look at some gameplay. Okay, so our game is a survival game in its core. It features a lot of the classic stuff you would see in a survival game, like having to fix food, you have to stay warm in a shelter, etc., etc. You start off small, and you craft simple weapons like rifles and pistols and other guns, and then as you progress through the game and you get access to more exclusive loot, you will have to build stuff like semi-automatic rocket launchers, tanks, armored vehicles, etc. The world is inhabited by massive hordes of zombies in this case. Thousands and thousands of them will try to kill you. And we really want this to be a good cooperative experience, so we've also focused a lot on the multiplayer. And we developed a demo last year where we tested this on a bunch of players. And what we found out quite early on was that these horde mechanics can turn into pretty interesting situations if the players do not cooperate, plan, and communicate correctly. Our goal is for the players to still feel immensely powerful. We want them to be able to slaughter hundreds and hundreds of zombies in a matter of seconds, but sometimes that still won't be enough. Sometimes when you are looting an urban area, for example, and you trigger one of these hordes, your only goal will to just get out of there alive so that you can get your loot back to your base so you can progress in the game. All of this takes place in a procedurally generated world. The game is tile-based, so everything in the world is built in tiles, which can have objects standing on them and walls surrounding them. The players are spawned randomly into this world, and they are free to their own device to explore and find stuff and loot urban areas and sites, and then upgrade their base. Everything in the game is also moddable, so we have exposed all of the content in the game in XML files that the players have access to. And this is not just an extra layer that we have added upon the game itself, it's something that we use ourselves in order to create the content. So for example, items in the game, all of the objects you see standing around in the world, weapons, vehicles, everything will be moddable. And also the algorithms defining how the biomes are generated in the world, etc. So let's head into the actual dots part of this session. In order to better understand what problems we faced, I have to just briefly talk about the architecture of our game engine. So basically, we use what is called an MVC pattern, a model view controller pattern. And what this essentially means is that the view is completely separated from the controller. You can also see the view as the game client and the controller as the game server. So in our case, everything that happens in the game, something explodes, projectiles are fired, things collide, the pathfinding for the zombies, for example, everything happens on the controller thread. The view then is updated by the server over the network with a subset of the model of the game model. And this is just the subset that the view really needs in order to accurately represent for the player what happens in the game. One of the things that we had problems with in the beginning was, of course, the pathfinding and the collision avoidance of all of these thousands of zombies, because each zombie is actually one individual entity. There is no abstraction in our game of a zombie horde. And it's the algorithms for the individual pathfinding and collision avoidance that makes them act in a horde-like manner. With the controller thread, we can actually run the server on just 5 ticks per second. And the view then interpolates all of the data so that it flows smoothly for the players. The important thing to note here is that it was in the view that we had the major bottlenecks before we started using dots, and it's where the dots has really shined for us. And this was specifically 2 particular implementations, which I will get to later. So first off, before we actually head into dots, we had to think about, does it make sense for us in our project? And actually, in our view, the entities that we simulate, all of these thousands of zombies, they are really simple. So they're actually quite easy to model in a data-oriented manner. So it fits our problem description very well. We decided to do this for 2 specific implementations, which I will talk about here today. The first one is the world objects. And the world objects is simply just static objects that stand around in the world. It can be trees, it can be rocks, it's all of the walls in the game, etc. And if we could transform these world objects into ECS first, and that would work very well, we decided that we will go on and look at the enemies as well. So, when we think in a data-oriented manner, what we have done is that we take a look at the object, in this case a tree, and we try to find out what is the minimal required data that we need in order to represent this object in our game. And for the trees in our game, the data looks something like this. We have 2 floats for the position, an X and a Y component, and also 1 float for the rotation, which is only for the Z axis. Because in essence, our game is a 2D game with 3D graphics. Then we need 1 float for the scale, and we need some 3D data because, of course, we want to be able to see the trees in the game. When we have made up this definition of the minimal data we need, we can then turn it into what is called an archetype. And an archetype is basically the ECS class, you could almost say. You use this in order to define what a tree is, and we use this as, when we instantiate a tree, we will do that using the tree archetype. In this case, you can see we have 2 sets of components, the first one being the unique components. And this is called a local to world component. This is basically a component that is shipped with dots, and it basically replaces the transform you would have in a mono behavior or a game object. It's a unique component because obviously all trees need their own position, their own rotation, and their own scale. We can also see that we have shared components, and in this case, this is the render mesh. And the render mesh basically contains the 3D model, the material, and that kind of data. And since in this example we assume that all trees have the same model and the same material, they will also have the same render mesh, so they all share a reference to this one. I will show you some code examples today, but I will really just blast through them because I won't have time to go into the details. I should also mention that the details are not the important part I will focus on in this presentation. It's more the general concept. But in this example here, we can see that we create the archetype, but basically specifying what components does a tree have, what data does it contain. When we instantiate trees using this archetype, the system will create what is called an archetype shank. And an archetype shank is basically just a pre-allocated space of memory where we will store trees. So even if we just instantiate, let's say, 7 trees in this example, the system will create an archetype chunk in the memory which can store, for example, 1,000 trees and just leave some of the spaces blank. An archetype chunk basically contains a set of arrays which contains all of the data for the trees in our game. So here you can see, for example, we have one array with the local to world component, which means that each tree is represented by an index in that array. We can also see that there is an entity array, and the entity array basically contains a unique ID for each entity in our game, and some metadata for deciding when the tree is living or when the space in the archetype chunk is free. So as you can see here, when we instantiate these 7 trees, they are just an index in one set of those arrays. So the 3rd tree will be index 2 in the entity array, the local to world array, etc. When we create an entity, it can look something like this. In this example, we first basically just fetch the model and the material from a prefab and set that in the shared component. We also decide what position, rotation, and scale the tree should have. And then we set the components of the instantiated tree in the bottom here. We do the set component for the unique data and the set shared component for the render mesh. This is what it can look like quite simplified when we want to instantiate a lot of objects. So in this example, we could say that the players have moved around in the world, and they have triggered the loading of 3 new map chunks. In this case, these new map chunks have 500 new trees standing on them, so we need to instantiate those. What the system will do is that it will find the first archetype chunk in our game, which has free space available, and then simply assign the new tree values to those 2 arrays I talked about earlier, the entity array and the local to world array. And this is, of course, extremely much cheaper than the traditional instantiation of game objects in traditional Unity programming. It's basically just equivalent to assigning a couple of values into a couple of arrays, and you have a new tree standing in your world. Destroying a tree is almost as simple. Let's say that the player has just chopped down a tree in order to gather some wood. This tree happens to be somewhere in the beginning of the 2nd archetype chunk, which we just added trees to. It's important that the free space is preserved at the end of the archetype chunk arrays. So what the system will do is that it will find the last living tree in the same archetype chunk as the tree we want to destroy. Then it will simply swap the positions between those trees and flag the tree we wanted to destroy as dead, effectively preserving the free space at the end of the archetype chunk and keeping the important data that we actually use tight and compact. So, to recap, when using ECS and dots, we want to think about objects as data, the minimal amount of data required in order to represent them. When we have this definition, we can create what is called an archetype. And the archetype is basically almost a class. It's a definition of what an object is, so that we can use that in order to instantiate objects. The archetype chunks are basically a set of arrays which contains the data for our objects in the memory. And instantiating an object is basically equivalent to just assigning a couple of values to these arrays and these archetype chunks, and destroying a tree is equivalent to swapping the position between 2 objects in these arrays and then flagging it as dead. So, this completely eradicated all of the problems we had previously with lag spikes. Because whenever the players would move around in the world, you would have these massive lag spikes because we would have to instantiate thousands of objects and destroy thousands of objects in one go. So that's pretty good, we thought. Let's go ahead and try to do the same thing for the zombies. If we can simply just get ECS to work for the zombies, we will not have to worry about spawning them and destroying them in large quantities. So I thought it would be a good idea to do this part in a table. So here we can see the pre-dots test. We would have 2,000 enemies, and that would be about 9 milliseconds of time it would take to update them each frame, which is, of course, a huge chunk of the 16 millisecond time budget we had. Then we will look at the ECS implementation, the ECS plus the job system, and finally also inject the burst compiler. And for each step, we will see what the performance gains were. As with the world objects, when we create the enemies, we have to also define what is the minimum data we need in order to represent an enemy in our game. So in our case, we need a position and a rotation, just like the world objects, a position rotation component, 3 floats. Then we also need a target position, because as I mentioned earlier, we use the MVC pattern, and the actual position of the zombies is on the controller thread on the server. And this means that the view have to be updated of this actual position and then linearly interpolate the positions towards this target position. We also need the 3D data, a model and a material. And then there's also a fourth thing called an enemy tag. We got 2 different enemy types in our game right now, small enemies and big enemies. And the only thing that differentiates their archetypes is this enemy tag. So it's basically just an empty component. Our small enemies have the small enemy component, the big enemies have the big enemy component, and the only reason it's there really is for us to be able to distinguish between these 2 kinds of entities. The most important thing, however, that the zombies have, that the trees do not have, is the system. And this is basically what replaces the update methods of mono behaviors in ECS. As you can see here, I've also marked the animation data and animation systems as orange, and that's because I won't have time to talk about those today. But there is a great example project you can look up online featuring a very efficient way to do animation instancing when you do ECS, made by Nordius and Unity in collaboration. So I would really check that out if you're interested in making your animations in ECS more effective. In traditional Unity, when we update zombies before dots, it could look something like this. The main thread would loop over a big list, like perhaps 2,000 zombies. It would then access each zombie and then call for an update method in one of the mono behaviors, the zombie script, so to say. And what this effectively means is that each zombie moves themselves around in the world from within. The biggest difference between this and the ECS system is that the ECS system is completely separated from the entities themselves. It can look something like this. To the left here, we have all of the archetype chunks in our game right now. We have a couple of archetype chunks containing trees. There are some rocks, and then there are 3 archetype chunks containing enemies. In our onUpdate function in this system, we have the code that takes the zombie's position and rotation and linearly interpolates it towards the target position and rotation that they have on the server. In order for the system to know which entities it will execute this logic on, we have to construct what is called a query. And a query is basically a description of the entities we want to fetch. In this case, we have decided that we want to fetch all of the entities in the game right now which have both a position and a target position component. And this will, of course, filter out all of the world objects because they do not have a target position, but it will fetch all of the enemies because we do not care about enemy tag and stuff like that. When we've decided what enemies to fetch, the system will basically fetch those using the query, put them into the system, and execute the logic that we have specified. The query can look something like this. In this example, we basically specify that we want all the entities, all the archetype chunks containing entities, which have all of these components. A transform component and a target position component. This is not even the main point, that the system is not part of the entities themselves. What makes ECS so powerful is that it is designed with the hardware in mind. And in order to understand why, I will just briefly explain how the cache works in the CPU. So this is a very simplified sketch of the cache memories and the RAM memory and the CPU. Closest to each CPU core, we have what is called the level 1 cache. And that's the smallest but fastest memory where we can fetch data whenever the core needs to work with it. So in this case, we fetch the position and rotation for one zombie, for example. If that position rotation component is within the level 1 cache when we fetch it, it will be an extremely fast operation. However, if it happens to reside in level 2 cache, that might be about 5 times slower. If it resides in the level 3 cache, it might be about 20 times slower. And if we're really unlucky, we have to go all the way back to the random access memory, and that can be over 100 times slower. And the important part here is not the details. The important part here is that to understand if we can use the level 1 cache as much as possible, our application might run potentially 100 times faster. And in order to understand why ECS does this so effectively, we have to look at cache lines. So whenever the CPU wants to fetch data that it has to work with, it will do this in what is called a cache line. And a cache line is usually 64 bytes. This is what it would look like in a game object before we started using dots. When we fetch the transform data for the position and the rotation, we do this in a vector 3 for the position, which has 3 floats. And we also fetch the quaternion for the rotation, which has 4 floats, which in total is 28 bytes. As you can see here, if we would loop over 1,000 enemies, we would load 1,000 cache lines into the CPU cache, our most valuable memory, and we would basically, more than half of it would be trash data that we don't need. And this is because in the transform class, we have the position and rotation declared first, and then we have a bunch of declarations for variables that we don't really need. In fact, it's even worse than this, because according to our minimal definition of the data we need, we only need 3 floats for both the position and the rotation, which means that when we loop over 5,000 zombies, for example, we basically flush the entire CPU cache, and 80% of it is trash data. If we look at the Archetype Shank memory instead, we can see that since all of the data is placed in arrays, it will align perfectly in the memory. And after the first position rotation component, there will be another position rotation component, another position rotation component, etc. And as we can see here, when we fetch a cache line using ECS, when we fetch the first position rotation, we will get 4 more position rotations loaded into the level 1 cache for free. And this means that when we continue looping over these arrays, the fetching of the data will be much faster. The CPU can also engage in what is called prefetching. It's not hard to predict when you loop over 1,000 enemies. When you have done the 5 first, what happens next? You will have 5 more enemies, and 5 more enemies, and even 5 more. So the CPU will start to recognize this pattern and start fetching 2 cache lines instead of 1 each go, which would of course be impossible if you look at the top example here of the game object, where we have a little valuable information in the beginning of the memory and then just a bunch of stuff that we don't really need. So, if we compare this result, before we use dots, each time the CPU would fetch a position and a rotation from a zombie, we would get about 12 bytes out of 64 possible. When we use ECS and prefetching is enabled, every time the CPU fetches a position and a rotation, we get 120 bytes each fetch. And this, just based on this very simplified theory, our game should be able to do this 10 times faster now. And if we look at the result, it's actually about 9 times faster than what we did before. So now we can have 2,000 enemies in the screen at once, and we can do that in 1 millisecond of time, which is, of course, really good. But even if we could stop here and be pretty satisfied with our goals, we'd still wanted to look at the job system and the burst compiler and see how far dots can really push this. So, the job system. The job system is very much like an ordinary system. Here we have an example. To the left, we have all of the archetype chunks in our game. Right now, the players might have played for a while, and they have triggered a horde encounter. So when we do our query in order to fetch all the enemies, we get 16 archetype chunks. These archetype chunks in the job system, or what the job system does, rather, is that it will take this full workload of all of these enemies, and it will divide them into smaller jobs, and then distribute them across all of the CPU cores. And it could look something like this. So in this case, it created 16 jobs, 1 for each archetype chunk, and created queues to all the 4 cores with 4 jobs each. Now, if, for example, the operating system has kept one of the core busy during this time, it might not be able to do the work as fast as the other cores would that had nothing to do. So what the system can then do is engage in what's called work stealing. And this is basically letting cores that have finished their jobs faster than other cores steal stuff from the other cores. And in theory, of course, this means that all the cores will work at the maximum capacity until the full updating of all the zombies is done. This is what it looks like in code. Basically, we do it in 2 steps. The first one is scheduling. So in this example, we have defined what arrays from the archetype chunk we want to use when we update the positions of the zombies. And we also prepare some other data, for example, time.delta time, some constant values for speeds, etc. And then we basically tell the system, for this group of archetype chunks, schedule these jobs, and distribute it over the course. And this is the execute function. So this is basically the code that we run for each of these jobs. And instead of being for the whole lot of zombies this time, this is on a chunk-by-chunk basis. So this code will basically loop over the arrays in one archetype chunk and update the positions of our enemies. With the job systems in, it improves the performance by an additional factor of 5. So compared to before dots, it's now 35 times faster for us to simulate the enemies in our game, which at this point has a result of 2,000 zombies in 0.2 milliseconds. And that's also really good. But the thing is that we can also inject the burst compiler. And what's so interesting about the burst compiler is that if you have just done your ECS in your job system correctly, it's extremely easily to get it to work. The burst compiler is the closest thing I've been to magic since I started coding 15 years ago. And I have a very limited understanding of exactly how it works and what it does. But in general, it allows us to declare for Unity to compile certain code snippets into extremely optimized machine code. And just to give an example of this, here we have a classic assembly example of adding two floats together. It will take one float and another float, add them together, and you will get the result. With the burst compiler, we get access to what is called single instruction, multiple data instructions, and it can look something like this. So it can, in one go, take 8 floats, add them to 8 other floats, and get 8 results. And of course, if all of these floats would be fetched from the random access memory, for example, the gain you would get from this kind of instruction is not that good. But since we have done our stuff in ECS, and most of our data is in the level 1 cache when we fetch it, this becomes extremely fast. My favorite thing about the burst compiler is how you implement it. So basically, all we have to do is to declare for Unity that we want to compile this certain code using the burst compiler, and it looks something like this. It's basically just an injection. And what about performance gains? When our CTO, Anders, showed me this the first time, it completely blew my mind, because the burst compiler takes this 0.2 milliseconds and turns it into this. We couldn't use 2,000 enemies anymore to make a good measurement for the time it took. So we had to bump it up to 20,000. And at 20,000, we do 20,000 enemies in 0.04 milliseconds, which is a performance gain of 2,250 times faster than before we started using dots, which is just insane. So, to recap, archetype chunks store data in arrays of data. And what this allows us to do in the systems, when the system loop over these arrays in order to execute logic on our entities, most of the data will reside in the level 1 cache in the CPU, which is extremely much more faster than if we would do it in an object-oriented manner, which would lead to more level 3 cache hits and random access memory fetches. The job system makes sure that all of these updates are executed on all of the CPU cores and hyperthreads that we have available in our hardware. And in theory, it should keep the processor at its maximum capacity throughout the whole job execution. The burst compiler further improves this by compiling our code into extremely optimized machine code. And it also targets the CPU architecture of the machine we're running at the moment. So if you run at different machines, the burst compiler will lead to different results, and it will make sure that you have access to all of the instructions available on that particular CPU. So let's take a look at a stress test. In these video clips you will see here, I'm not sure about the exact amount of zombies, but it's about 5,000 to 7,000. And in general, we run at a pretty fairly stable 60 frames per second, which was our goal. There are still some problems. You might notice there are a couple of frame drops here and there, but that's mostly due to garbage collection spikes and other things that we have to work on going forward. But the 60 frames per second goal can be said to be pretty met. If we would run this before we implemented dots, it would completely trash even a fairly high-end computer. So, are game objects dead? And this was one of the questions we asked ourselves before we started using dots. Do we have to rewrite our entire code now and make it into dots code? And that's not simply the case. A lot of the stuff in our game are still game objects. The player is a game object. The vehicles are game objects. Even world objects that have light sources or particle systems attached to them are game objects. And a dots hybrid is viable. We have implemented an infrastructure in our game that allows us to create objects that are either ECS entities or game objects without even thinking about it. So when our content creators and artists go into our code and want to create entities, they don't have to think about dots. They can basically just put in their 3D mesh, create an entity in the XML I showed you earlier, and there's a Boolean there that you set, true or false, if it's an entity or a game object. And in general, we want to really encourage everyone to think in a more data-oriented manner, not to think about objects as a human intuition perhaps would do, like an object is a set of components that all have their own logic executing, etc. But actually designing our code so that designing our code with the hardware in mind. Yes, so basically, I would really encourage all of you to try dots if you've been thinking about it and have been a bit hesitant. Because maybe if you're successful, all of your performance issues could quite literally almost be completely gone. And that's pretty much it for this presentation. So if you have any questions or want to discuss this, the easiest way to do that, or the best way to do that, is to communicate directly with us on our Discord. So you can find us on Twitter, and there you will find a link to our Discord server. You can also just send me a mail, and I will try to answer the questions as well as I can, or I will simply forward them to our CTO, who will happily help you with that. Thank you.